Hi dear students, welcome to Riju and PSK online classes. We are in a new world of semiconductors, okay? And the problem with the chapter is that the language is new, the terminology is new, the technology is new. But the advantage is that you have been using this practically personally for a long time. And this world without electronics will be a very boring world. You wouldn't be using a mobile phone, wouldn't be watching a TV if this thing stops working. Alright, so in the last class we started the basic of this chapter 14. I said it has the longest name, chapter name, okay, and I also asked about those fruits question. I am not showing that visuals again. Why are you after that semi-ripened fruit even though you have very ripe and very raw fruits available? Okay. Now the basic points that we studied in the previous 3 classes are like energy bands. Hope you can define energy band. Range of energy possessed by electron. Valence band, range of energy possessed by the outermost shell electrons. Conduction band is the range of energy possessed by free electron, which is actually the conducting electron. And the forbidden energy gap. In normal cases, electron can have valence band energy or conduction band energy, nothing in between. Okay. That's why it's called forbidden energy gap. And we know, according to the forbidden energy gap, we can classify materials. Because in the forbidden energy gap, if this is too large, producing conduction electron will be difficult. If this is small or zero, producing conduction electron will be easy. That is a basic concept. Okay. Now, the energy gap, if you want to calculate in a question, it is EC minus EV, where EC is the lowest conduction band energy and EV is the highest valence band energy. Now, the conductivity of a material depends on this energy gap, of course, and you can produce, you can create, you can separate an electron from valence band to the conduction band by giving energy, by heat, light or electric energy. These were the ideas, fine. Now, how do we classify materials based on energy gap or the energy band? Metals, you can draw the diagram like this or like this. I explained that one. For a metal, energy gap is 0. That means at room temperature, you get a large number of electrons for conduction. Insulator has got a large energy gap. Large means, see the unit is 3 electron volt. If it is more than 3 electron volt, then that is an insulator. It cannot produce enough number of electron in room temperature. So the plastic I have in my hand here has got an energy gap which is greater than 3 electron volt. Okay. That is why we use insulators, like for a wire carrying current we use a plastic insulator just because of this thing. Okay. If the energy gap were less than that one, then the plastic would start conducting at room temperature. Semiconductors are hero. Oh, I love these things. Okay, I'm in love with semiconductors. Because without that, the world wouldn't be like this. My mobile phone will be dead. It will be like a brick. Semiconductors, energy gap is less than 3 electron volt. The prominent semiconductors that we use are silicon and germanium, around 1 electron volt. The energy gap for both silicon and germanium is around 1 electron volt. Fine. So semiconductors has the advantage that if you increase temperature, their resistivity will decrease, conductivity will increase. Then I said about a very novel, not a novel corona, novel idea. A novel idea about Hall. Hall is a vacancy of an electron which can be considered as a positive charge. It can't move physically, but due to the shifting of electron, this will appear to be moving. We classified pure semiconductors and impure semiconductors. Pure semiconductors are also called intrinsic semiconductors. This contains only one type of atom. Silicon will have only silicon atom. Germanium will have only germanium atom. And the drawback of intrinsic semiconductor is that the number of free electrons are less. You need to depend on the temperature to produce conductivity, and no important devices can be made out of this. Okay, and ultimately that's what we want. We want to make some devices which will help us in our life. Fine, technology. So this is not possible with the intrinsic semiconductor. Okay, these are the basic points, and due to that you cannot make a device. That's the point. Okay, so this mobile phone contains a large number of electronic devices, and all of them are not made of intrinsic semiconductor. That's the point. Okay, so what is the solution? Solution is drugging. Okay, take a drug, enhance your abilities. Doping is a process of adding impurity. If you add impurity to pure semiconductor like silicon or germanium, then the conductivity can be modified. This is where we have the answer for that fruit problem. You cannot do this with a metal, you cannot do this with an insulator, but you can do this with a semiconductor. You can control its conductivity. Little later we will study, we can create a device which will conduct only in one direction, not the other direction. It will conduct only in one side, not the other side. Interesting. That is why we are after semiconductors. Okay. I think I answered that question. I have been asking in the last 3 classes. Okay. Why are we after semiconductors? The reason, by doping we can control their conducting characteristics. Simple. Don't you think so? Now, doping can be done in 2 ways. See, the normal semiconductor has got a valency of 4. So, we can call it as tetravalent atom. And we can take pentavalent or trivalent impurity. Pentavalent you can take arsenic example, trivalent as an example you can take indium. If you add arsenic or indium, then the conducting characteristic of this this material will change. That's what we call extrinsic semiconductor. That means the quality of this semiconductor is extrinsic. It comes from external. That means it comes from that dopant material. Okay. Now, we divided extrinsic semiconductor into 2. One is known as N-type, the other is called P-type. We were discussing about N-type, and how do we make N-type semiconductor? N-type semiconductor is prepared by doping tetravalent semiconductor by pentavalent impurity. Pentavalent means arsenic, antimony, phosphorus, etc. You mix this arsenic with semiconductor silicon, then you get a N-type semiconductor. Now, how does it work? How does it work? I said that there is a 5th electron. In the covalent bond structure, if you put the pentavalent impurity atom, it's the 5th electron. Whose 5th electron? The 5th electron of the pentavalent. For example, arsenic atom, that will not form a covalent bond. Understand that will be still orbiting arsenic nucleus, but that is not part of covalent bond. So, if you look into the 5 electron of outermost electron of arsenic, what is different? Out of the 5 electrons in the arsenic atom, okay, 4 are in the covalent bond. The 5th one is not in the covalent bond, but of course it is in the valence shell. Therefore, it is little more free than the other 4 electrons, but it is not as free as a free electron. See the situation. This 5th electron is not a completely bound electron. It's more energetic than the bound electron, and this is less energetic than the free electron. So, its energy comes in the energy gap. Normally, this is not possible. It's forbidden. Normally, it is forbidden, but this is possible. So, this 5th electron will make all the difference. That 5th electron can be utilized for conduction. Normally, this can be represented like this one. Okay, I can give you one more idea. That after doping an N-type semiconductor, okay, as you can see that here, an N-type semiconductor, if you see, there is a free electron and there is a core. So, there is a positive core and a free electron. This is a 5th electron. So, this is how generally we represent an N-type semiconductor. That's given in NCERT textbook like this one. Okay. Now understand that this negative charge and this positive charge tells you that the total charge is 0. The total charge of the system is 0. What will happen if I remove this electron? What will happen if I remove this electron? If I remove this electron, this will become a positive charge. With that electron, this is neutral. Okay. That is obvious, right? This is your arsenic atom. Arsenic. Arsenic has got how many electrons in the outermost shell? It has got 5 electrons in the outermost shell. Is it neutral? Of course, arsenic is neutral. Okay, and I am talking about only this particular electron because this is not part of covalent bond. That is why it has got a special position. The remaining thing is part of the arsenic atom. And if you remove one electron from this one, what will happen? This will become singly ionized. Singly ionized means it will have a positive charge, one charge of an electron. So this negative charge of electron, this is minus E and this is plus E, the total charge is 0. So you cannot remove the nucleus, but you can remove this fifth electron. If you remove the fifth electron, then what will happen? You will get a positive ion. That's it. Okay. So this picture is very, very important for your coming discussions. N-type semiconductor means, if you ever see N-type semiconductor, then you have to see there is a positive core and there is an electron. There is another positive core, there is an electron. There is another positive core, there is an electron. And what are these electrons? These are the fifth electron of that impurity atom. Here, example, arsenic atom. Fine, this is what we see. Now, if one electron is lost from here, then this will become positively charged immobile ion, because these are the atom, they can't move around, because in a solid they are fixed. Okay. So this is a picture that you have to keep in your mind. Alright. Now, the terms, technical terms, donor atoms. What is the meaning of a donor atom? Here the fifth electron is given by arsenic. So arsenic atom is called donor atom. Pentavalent impurity atom is called as donor atom. What is donor level? Donor level represents an energy level. The energy level of that fifth electron. Where is it? Is it in the valence band or is it in the conduction band? Energy of the fifth electron, is it in the valence band or is it in the conduction band? What's your answer? Answer is, it's not in the conduction band because it is not a free electron. It is not in the valence band because it is not as bound as the other electrons. So where is this energy? This energy is in between. It is in between, not in the conduction band, not in the valence band, a little lower. How much? 0.001 electron volt, very small value. So this is the position of the fifth electron. See, this is important to understand. This is important. I am repeating this because these are the foundation points. Okay. If you actually want to remove an electron from here to there, from valence band to conduction band, the minimum energy, so see, if you want to remove an electron from this level to that level, the minimum energy is equal to energy gap. But if you are trying to remove an electron from this level to the highest level over there, you need more than that one, right? But here if you have the fifth electron, the pentavalent electron, then you need only this much, its position is here. So you need only this much of energy. Okay. In the structure I will say, this is your arsenic atom. This is making covalent bond with the surrounding silicon atoms. Okay. This is one way of representing the covalent bonds. Arsenic has got how many electrons? 5 electrons in the outermost shell. And out of that, one electron will go here, one will go here, one will go here, one will go here. Where will the fifth electron go? The fifth electron has no place to form a covalent bond. So fifth electron is here. See, a bond means a force, extra force on that one. Okay. This electron is under the control of this arsenic nucleus as well as the covalent bond structure. So this is more tightly bound. This is tightly bound. That is tightly bound, this is tightly bound, this is tightly bound, this is tightly bound. What about this one? This one is loosely bound. It is loosely bound. But is it a free electron? Loosely bound. Okay, loosely bound, not free. That's an important point. It is loosely bound but not free. If you want to see, these electrons are represented here. But this electron is represented here. It has got a more energy. Right? So if you want to make I want a free electron, so what is the best thing I can do? Should I try to remove this electron to make it a free electron or this one? If I want to take this as a free electron, I need more energy. But this one, little energy. So that is the advantage. With every arsenic atom, I will get one electron which is very easily available to make a free electron. This is the idea. What is the advantage of doping and making an n-type semiconductor? Answer: with every impurity atom, you will get one electron which can be easily made into a free electron. Number of free electron controls the conductivity, right? So if you want more conductivity, you want more free electron. So if you want more free electron, you can add more arsenic atom. So the amount of arsenic atom added will increase the conductivity. How to increase conductivity of a semiconductor? One point, not practical, it is by increasing temperature. Second point, very practical, dope it. If you want more free electron, dope it. Use pentavalent. With every arsenic, you are getting one electron. Fine. Now one more point. Look at this diagram. These diagrams, these white dots represents electrons. Those white dots represent electrons in the valence band. Okay. So these white dots are representing electrons in the valence band. Electrons in the valence band. Okay. Now, by giving energy, I can remove this electron to this level. That was the point. Thermal agitation. Fine. But here you don't have to do that one. What to do? Even before this can shift, electron from the arsenic atom can become free electron. Electron from arsenic atom. So what are these electrons? These are of two types. Look at the diagram. This is representing a hole. This is a hole. A hole is created because electron absorbed energy from somewhere and become an electron hole pair, and that electron went here. So this is the electron thermally generated. So this is a pair. Okay. So that is given one thermally generated electron hole pair. So this is the hole and that is the electron thermally generated. And what are these white dots? These are electrons in the valence band. So what are these white dots? Those are electrons, free electrons. But from where did they come? They came from the pentavalent impurity. So I can say these are pentavalent impurity electrons. So this diagram is very important. Look at the diagram. In NCERT, the color will be different, but still the idea remains same because the same diagram in NCERT. One thermally generated electron hole pair. There is one thermally generated electron hole pair. Then count here 1, 2, 3, 4, 5, 6, 7, 8, 9. These 9 electrons come from impurity. And one arsenic will give you only one electron. So how many arsenic have been added here? 9 arsenic atoms, or 9 pentavalent atoms are added as per this diagram. Is this okay? Pakka? One hole, one electron. It's a pair thermally generated by absorbing thermal energy. All the remaining one come from doping. So see the number of hole is only 1, but the number of electron is 10. Number of hole 1, number of electron is 10. That is why we say the number density of electron is much greater than the number density of hole in an n-type semiconductor. So we will say electrons are majority carriers. Electrons are majority carriers. What carriers? Majority charge carriers. Majority charge carriers. And holes are what? Holes are minority. Holes are minority charge carriers. I'll tell you one important point. What is it? You studied that by absorbing thermal energy, they can be separated as electron or hole pair, but they can also recombine. I told you they can recombine and they can release energy. Okay. Now see, here number of electron become very high and number of hole is very less in an n-type semiconductor. So when the number of electron increases, the possibility of electron hole recombination will also increase. When the number of electron increases, the rate at which electron combines with hole will also increase. Because earlier in the pure semiconductor these numbers were equal, but now one hole will find so many electron around it, or maybe so many electron will look at this hole and they are ready to jump into that one. So this here 10 electrons are there, one hole is there, so the chance of recombination is more. Suppose you have only one hole and one electron, then the chance is very less, but here you have 10 number, so the chance increases 10 times. Therefore, listen carefully, I told you in n-type semiconductor Ne is much greater than NH, and we say electrons are majority charge carriers and holes are minority charge carriers. Is that okay? Right. Now let us move back a little bit. First point, in a pure semiconductor, Ne equal to NH, and that was we call as Ni the intrinsic carriers. So if you multiply Ne and NH, what do you get? If you multiply Ne and NH, you will get Ni squared. But now in n-type semiconductor, Ne is much greater than NH. Refer the diagram, think about it. So the rate of electron hole recombination will increase. That means more holes will get occupied. This will effectively decrease NH. NH will decrease from this previous value. NH will decrease. That means the new NH will be less than Ni. And Ne is more, NH decreases. Understand? So when you dop it with the pentavalent atom, the number density of electron will increase, but the number density of hole will not remain the same, it will decrease because of the more combination. But the product Ne into NH, that will remain same. So when you dop a pure semiconductor where Ne was equal to NH, when you dop it, Ne will increase and NH will decrease because of the rate of electron hole recombination. So this equation, where is it applicable? Is this applicable only in intrinsic or pure semiconductor? No, you can say no, this is applicable for every semiconductor. Both intrinsic and extrinsic, you can apply this. For intrinsic it is applicable, for extrinsic this is applicable. Okay, that is it. It is because of the number of holes. Okay. Now that is it, Ne is greater than NH, these are the things, Ni square equal to NEH, I discussed that point. Now how does it conduct? This is very important. How does it conduct? The conduction of a pure semiconductor. In a pure semiconductor, you can look like this. Okay. Oh my God, my slide got changed, no problem. Okay. Consider an n-type semiconductor. In an n-type semiconductor, you have large number of electrons. These are electrons. Large number of electrons are there. You saw the previous slide. There were 10 electrons but one hole. And there will be minority carriers, holes. Few number of holes. Okay. Now, what will happen if you give a battery connection like this? This is the positive side, this is the negative side. Higher potential, lower potential. This will create an electric field in the material. This is positive side, this is the negative side, and electric field will be created like this. You studied that a charged particle will experience a force in an electric field, F is equal to Q into E. And for a positive charge, force will be in the direction of the field. And for the negative charge, force will be in the opposite direction of the field. So these electrons will experience force opposite to the field like this. So they will start moving. These electrons will start moving in this direction. Motion of electron in this direction will produce a current. And the current of electron will be in this direction. This is the electron current. What about the holes? Holes cannot move, but I told you that last class, okay, holes cannot move. One valence electron, these are free electrons, but one valence electron can jump to this hole. So this hole will effectively jump to the other side. one valence electron can jump to this hole, this hole will move to the other side. So effectively holes will move in this direction. Just like what we discussed in the case of intrinsic semiconductors, electron will move opposite to the electric field, holes will move in the direction of the electric field, but both will produce current in the same direction. Both electron current and hole current are in the same direction. See the direction. Okay. Just like in the case of intrinsic semiconductor, in an extrinsic semiconductor also there will be two currents. One is due to electron, another is due to hole. But see, the number is not the same. Therefore, there will be a large electron current and very small hole current. Both are in the same direction. The total current flowing will be equal to, the total current is nothing but IE plus IH. The total current is IE plus IH. What is the advantage of making n-type semiconductor? Reason is simple. By adding more pentavalent impurity, the number of electrons can be increased and the electron current can be increased according to our will. This is the advantage. Alright. So there will be two currents. Understand that electron current and hole current. Both are in the, currents are in the same direction, but their motion are not the same. Now current is generally independent of temperature. Of course, temperature variation can affect current, but not much. Okay. Current depends on the doping concentration. That's a very good advantage. If you increase the doping concentration, you can produce more current. Now studying p-type semiconductor will be very easy. How do we define n-type semiconductor? It is a semiconductor produced by doping tetravalent silicon or germanium with a pentavalent impurity atom. Each pentavalent atom will give you one additional electron. Is that okay? Now, so dear children, study this part, read NCERT clearly, because NCERT beautifully these things are written. Please study that one. You study n-type semiconductor, then in the next class I will be talking about p-type semiconductor, but that will take only 5 minutes for that one because the ideas are very similar. Okay, so please prepare like that one and we will see in the next class. See you.